Hello, this is our presentation of quantitative construction planning and optimization research for the binding of Hainan Shidai water plant. My name is Bai Sixian, and this is content of our presentation. And now I will give a speech of the background and the literature review of this project. Right now, the existing water supply system just cannot keep up with the bottling needs. On top of that, the old water networks in towns and villages were built to lower standard and haven't been properly maintained for years. Once it's finished, daily water supply will get a big boost, and we will finally resolve the long-standing problems of low water pressure and inconsistent supply and the water quality issue across the area. The county government is planning to build a new water plant that can produce up to 42 cubic meters of water per day to handle the region's water needs for the next 2 decades. The project includes everything from water intake systems and the pipelines that carry the water to the purification plant itself and the pipes that deliver clean water to homes, plus all the supporting facilities. This project is expected to cost around 1.2 billion Hong Kong dollars and will take about a year to build. To make sure everything stays on track, we are using a linear programming model to smartly manage resources as things move forward. Because this project involves a lot of back and forth between civil works and the mechanical and the electrical installation. That's the reason why we've based our references on studies that use simulation and the cost analysis to optimize how wastewater treatment plants are designed and run, which has been shown to cut down their long-term cost. There is solid evidence that using smart time-saving strategy in water plants construction can boost economic return without sacrificing quality. Okay, now let my teammates Louis Ray talk about the work decomposition and the quantification. Thank you.
Thanks for Bai. Now let's go to the second part, the work decomposition and quantification. At the beginning of the work, we need to have the work breakdown structure. We need to divide the project into 4 levels. The level 1, project overall. We need to represent the complete Shidai water plant and water distribution network project. And the level 2, the major phases. We need to divide the project into key engineering phases, such as pre-priority work, water intake, and damage construction. And the level 3, subsystem. We further break down the main phase into the specific function system or construction section. And the level 4, the work package. We need to define the smallest executable task, and each task is assigned a unique code for tracking and management. And as you can see in the left of this page, it's the work breakdown structure diagram. After that, we need to estimate the workload. And now I will show you about the work package B as an example. And as you can see in the left of the page, it's the activation of the foundation piece for the clear water tanks and the drainage and sludge discharge tanks. And the excavation dimensions is 50 meters long in length and 30 meters in wide and 6 meters in depth. And we need to consider in the slope release and the earthwork volume of this working phase calculation coefficient about 1.1. And then we can calculate the engineering quantity. It's about 9.9 thousand cubic meter. And then we can also calculate the comprehensive unit price, about 85 Hong Kong dollar per cubic meter. And then we can get the total cost of the package B, about 841 Hong Kong dollar. And it's all for my part.
I will now walk you through our construction schedule estimating using the main sculpture work as a representative example. We began with 2 key scope elements, the base slab for the filter beds and the sedimental tanks covering 3,000 square meters, and the main reinforced concrete sculpture, totaling 6,151 cubic meters, which includes the base slab, side walls, and the roof slab. Based on Hainan's local water standards, the typical productivity for base slab construction is 1,000 square meters per day. Therefore, the base slab requires 3,000 divided by 100, resulting in 30 days, a duration with very limited room for compression due to its fixed efficiency. For the main sculpture, under conventional methods, the required time would be approximately 35 days, calculated from a productivity rate of 94.63 cubic meters per day. However, according to documented projects, a practice in Hainan, recent water supply projects have achieved a 47% improvement in construction productivity for concrete main sculpture compared to traditional approaches. This efficiency gain and by adding a second construction crew, we can compress the main sculpture duration from 35 days down to 25 days. So as a result, the total project duration is reduced from 65 days to 55 days. Thank you. I will now hand over to my teammates for the next part.
Let me talk about the project schedule using the AON diagram. First, we did a forward pass. The main idea here is the task can only start once all its predecessors are finished. So the earliest start time for a task is based on the latest earliest finish time of all the tasks that come before it. From this calculation, we found that the total project duration is 365 days. We also got a clear view of how long each pass in the project takes. Next, we did a backward pass. The key question here was, what's the latest each task must start and finish to keep the project on track for 1 year? By comparing the earliest and latest time, we found the slack for each task. The path where slack is 0 is our critical path. So our critical path is A, B, E, M, Q, R, W, A, G, A, K, A, L, A, M, A, N, A, Q, A, O. Any delay on this path will directly delay the whole project. In an AOA diagram, the arrows represent the tasks themselves, and the nodes are event points in time, like the start or finish of a task. The horizontal lines of each arrow represents that task's duration. The logic is similar to an AON diagram. This diagram is built using each task's normal time. You will notice the dashed arrows here. This represents slack after a task is finished. The length of a dashed arrow shows the amount of slack available. In a Gantt chart, each horizontal bar represents a task, and the length of the bar directly represents to the task's duration. You can see at a glance, when a task starts and ends, which tasks are running in parallel. The tasks on the critical path, which I have highlighted here in gray. These are connected back to back from start to finish with no slack. For the non-critical tasks, I've used the blue bars. This means these tasks can be delayed within that time without affecting the final project deadline.
Now, turning to my part, which is the optimization analysis of the project progress. Now, to begin with, we extract all necessary data from the provided AON diagram and the project information table. This allowed us to determine the key constraint for our model, including the range of the compressible days for each activities and associated crash cost per day relative to their normal duration. With this foundation, we set the boundary condition and define our decision variable, familiar X for the active scheduling and Y for the available crash time. Our object function is straightforward. To minimize the total project cost, the main constraints we incorporate are the maximum amount of the time an activity can be crashed, the precedence relationship ensures the earliest finish time for each activity is respected, and the non-negativity for all variables. The model was built and analyzed using the Lingo. We input and simplified the data table for the 41 project activities from A to AO to streamline the computation process. We can see that the Lingo proposal solutions after 13 days compression will cost 4,867,000 Hong Kong dollars. The result from this optimization gave us a clear, cost-effective strategy for compressing the project schedule. That concludes my section. Thank you.